Cloud speed is your gateway to AI and the cloud. Get up to date with recent trends in cloud computing and AI. In this project, we want to create a full-stack chatbot running a DeepSeek model. We'll be using a few key services to make this happen. AWS for hosting our Kubernetes cluster, container image, and a remote server to help us configure the EKS cluster. Ollama, an open-source tool that makes it easy to run AI models locally, whether on your computer or a server. FastAPI, to build the API layer that connects our DNS with Ollama. Langchain, for setting up the front-end application that communicates with our custom FastAPI backend. And Streamlit, for creating a simple, clean, and interactive front-end interface. Now, before we go any further, if you're following along with this project, just be aware, you will be charged for the EKS cluster. All right, let's get started. First, we'll create an IAM role for the EKS cluster. This role allows the cluster to access other AWS services. Make sure it has these permission policies attached: Amazon EKS cluster policy and Amazon EKS service policy. By default, the Amazon EKS service policy might not be included, so we'll need to go back and attach it manually. We'll name this role Amazon EKS Auto Cluster Role. Just select the role, search for Amazon EKS service policy, and click Add Permission. Next, we need another IAM role, this time for the EKS node group EC2 instance. This role allows the node group to interact with other AWS services as well. Look for and attach the following policies: Amazon EKS worker node policy, Amazon EKS _ CNI _ policy, and Amazon EC2 container registry read only. Sometimes, the predefined permissions don't include everything we need, especially Amazon EKS worker node policy and Amazon EKS _ CNI _ policy. So we'll add those directly. We'll call this one Auto EKS Auto Node Role. Select it, search for the missing permissions, and attach them manually. Now, let's create an EC2 instance. We'll use this to interact with AWS from the command line. You could technically use your local machine or AWS Cloud Shell, but Cloud Shell isn't ideal here. That's because we'll be building a DeepSeek Ollama image, and Cloud Shell just doesn't have enough memory or disk space for that process. As for my local machine, I'm not using it because I don't want to deal with cleaning up all the leftover files afterward. So yeah, we're going with an EC2 instance. We'll name it Access and use a t2.micro instance type. Create a key pair named Access and download it to your local machine. For the security group, make sure both SSH and HTTPS rules are selected. Also, set the storage volume up to 20 gigabytes, just to be safe. Looks like we're all set. Let's go ahead and launch our instance. All right, the instance has launched successfully. Let's open it up. According to our documentation, The next step is to move our project files to the EC2 instance. Make sure to replace the IP address in the command with your EC2 instance's public IP. Also, confirm that your key pair file is in the correct directory, and that the command reflects this. Now, let's quickly go over some of the files we're transferring. We forgot to update the IP address. That's why we're getting a connection timed out error. Just type yes to approve the connection when prompted. And now, the files are being copied to our EC2 instance. Once the transfer is complete, we can clear the screen and then SSH into the instance. Again, don't forget to replace the IP address and key path in the command with your actual details. Next, let's install the AWS CLI on our instance. Go ahead and update the environment first. We'll need the AWS CLI to access our AWS resources directly from the command line. We'll also need a user account with the appropriate permissions. In my case, I've assigned administrator access to the user. Not the best practice, to be honest, but for the sake of this video, it just makes everything smoother. Of course, in a real work environment, you should only assign minimal necessary permissions. Also, just so you know, I'll be deleting this user before the video goes live. Now, let's configure the AWS CLI. Grab your access key and secret key. Make sure to keep them safe. I'll delete mine after recording, just to avoid any security issues. I'm using the region US East 2, and we'll set the output format to JSON. With that, we've successfully configured our AWS CLI, and we're ready to interact with AWS services from this instance. Next, we'll go ahead and create our EKS cluster. Copy the command from the docs, then modify the necessary parameters. Let's clear the screen real quick, and then tweak the command to suit our needs. We'll rename the cluster to DeepSeek. Copy the EKS cluster role, ARN, and paste it into the command. We'll also need a subnet ID. You can find that on the VPC page in the AWS console. Pick one security group from your list. We'll add its security group ID to the command, and you can find that on the EC2 page. Now, while you can create the security group using the AWS Management Console, our main reason for creating the EKS cluster from the command line is to avoid permission issues. If you create the ECR repository from the console and then use a different user to configure it from the command line, you may run into problems when setting up the node group. So it's best to create and configure everything from the command line using the same user throughout. Please confirm that you've added all the required resource IDs correctly. Now you can go ahead and run the command. Go to the EKS console dashboard and confirm that the cluster is being created. You can also open the ECR section in the console, just to verify that no repositories exist yet. Now jump back to the command line and run the command to create the ECR repositories. We're creating two of them, one for the FastAPI image and another for the Ollama image. We'll name the first one Ollama and the second one FastAPI. Now let's install Docker on our EC2 instance. We're doing this because we'll be building the images directly on this machine. We'll move through this part quickly. What we're doing here is installing Docker, starting the Docker service, enabling Docker to start on boot, adding Docker permissions to our current user, and making sure the Docker Compose file is accessible to that user. Once that's set, confirm that Docker is installed. Then log out and log back in to apply the permission changes. Now we can go ahead and build our Docker images using the Docker Compose files, one for FastAPI and the other for Ollama. After building, don't forget to tag your images. Tagging is important. It tells ECR how to identify and store the image properly. Next, you'll want to confirm your caller identity, just to make sure you're logged into the right IAM user, one that has access to push to AWS ECR. Once confirmed, authenticate to ECR, and you're good to go. Now we can push our images one by one to ECR. After pushing, you can verify the uploads from either the AWS console or directly from the CLI. Let's take a quick look at our ECR repositories. And there it is. You'll see the image has been pushed successfully. We didn't assign a specific version tag to the image, so it just shows up as latest. In a real production setup, you'd want to version your images. That way, you can roll back easily when needed. Let's clear the screen. Now, we're going to grab the image URIs. These are what we'll use to update our deployment files for both FastAPI and Ollama. Starting with Ollama, open the Ollama deployment file in the servers directory. Replace the existing image with the ECR image URI you just copied. Double-check to make sure it's correct, then save and close the file. Next, open the FastAPI deployment file, again from the servers directory, and update the image URI there too, using the one from your FastAPI repository. Make sure it's the right one, then close it up. Now we need to download kubectl and give our user the necessary permissions to execute it. Now we need to download kubectl and give our user the permissions to execute the files. kubectl allows us to run command that will be executed on our Kubernetes cluster. So basically kubectl is the command line for interacting with our Kubernetes cluster. We would quickly move through this commands and confirm kubectl is installed. Next, we should update our kubeconfig file, which tell our AWS CLI which cluster we want to interact with. Next, we set our context if it's not set already. This tells kubectl the cluster we want to execute our commands with every time we execute our commands. Now we're ready to create our node group. At this point, we already have a control plane. That's the server our Kubernetes cluster runs on and uses to manage everything. But now we need the actual nodes, the machines where our workloads will run. This node group should be high capacity. Unlike earlier, where we used just a single container on the EC2 instance, this time, our node group might be running multiple pods for each service or deployment, depending on the load. So we need enough power to handle that. For this project, 30 gigabytes of storage will be enough. Let's go with Amazon Linux 2023 AMI and choose the instance type our 4.2 extra large, which gives us 8 vCPUs and about 61 gigabytes of memory. For storage, we'll set it to 20 gigabytes since we don't need a huge amount. Now, let's set the desired size, minimum size, and maximum size for the node group. I'm keeping the number of nodes low for this video, but in a production environment, you'd likely need more, depending on your traffic and workload. After reviewing our configuration, click Create. As you can see, our EKS node group is now being created. You can track its status from the AWS console or use the CLI. It usually takes a bit of time to provision the nodes, so feel free to skip ahead and check back once it's ready. Once it's done, run kubectl nodes to confirm everything's in place. Great, our node is now ready. Now let's create the Traefik service account. This gives the Traefik ingress controller permission to interact with the Kubernetes API. It allows Traefik to discover routes, services, and endpoints, so it can properly route external traffic into your in-cluster applications. Next, we'll install the Traefik CRDs, or custom resource definitions. These are used to extend Kubernetes with Traefik-specific features, like advanced routing, which goes beyond standard ingress resources. And always remember to verify that your installations were successful. Once that's done, you can go ahead and start your application by creating your services, deployments, and ingress resources. Make sure you follow the order specified in the documentation. We've now successfully created the required resources, and everything should be up and running. Of course, the only way to confirm that is by checking. We'll run a few commands to make sure the resources are active and healthy. Now, if you take a look at our other services, you'll notice they're using cluster IP, which means they aren't accessible from outside the Kubernetes cluster. But for the Traefik service, it's different. We've got a load balancer set up, and that comes with a DNS address. This is how we'll access our deployments from outside, based on the routes we've defined in the Traefik config. Let's go ahead and get the ingress service and confirm the DNS it's been configured with. We've also confirmed that our pods have been created successfully. Now let's make sure our deployments are running without any errors. Ollama is running just fine. FastAPI is up and running too. But we've got an issue with the Traefik deployment, and I'm pretty sure it's a DNS-related problem. Let's try to sort that out. First, we'll check the external IP associated with our Traefik service. And yes, Traefik is using the same DNS from the load balancer we saw earlier. Let's check the DNS to see which IP address it's associated with. We can also jump into the AWS load balancer console, find the DNS name, and confirm the associated load balancer that was created internally by our Kubernetes cluster. You can take some time to explore the cluster from the console, check out your node groups, compute capacity, services, and deployments. I'll skip through that here, but feel free to explore on your own. Next, we take the IP address that's tied to the Traefik ingress DNS, and we'll update it on our DNS provider. In this case, it's GoDaddy. After updating the record, wait a little, maybe a minute, and confirm that it's been propagated. Remember earlier when we tried to access the API and ran into an error? That was coming from the Traefik service. and it was due to DNS issues. If we run the nslookup command on our custom domain, it should now return the IP address of our load balancer, and that's exactly what we want. That earlier error was likely caused by SSL certificate issues, and it happened because we tried accessing the API before setting our DNS to point to the load balancer's IP. So if you run into the same issue, just know it's probably because the DNS wasn't set up before traffic was started. What you need to do is update the DNS record properly, then restart your traffic deployment, and it should work just fine. Let's test it by accessing our API using the DNS we set up earlier. Okay, it works. This is the root of our domain, and you can see the response. FastAPI is running because we're hitting the default route. To actually query our DeepSeek model running on Ollama, we go to this generate route. We pass in a simple prompt, in this case, say hi, and we got a response. You might notice the markup in the output, and that's because DeepSeek is a thinking model. But for our application, we don't really care about the thoughts. We're just interested in the final output. And the response here is, hello, how can I assist you today? Perfect. The API is working exactly as we wanted. Now let's take a look at the FastAPI_Ollama.py file to see how the route is set up and what the FastAPI app is actually doing. As you can see, the model we're using is called DeepSeek-R1-7B. When we go to the root route, which is just a /, FastAPI responds with FastAPI is running. It doesn't do anything else, and that's exactly what we saw earlier. To interact with the DeepSeek model via FastAPI, we use the /generate route. This sends the user's prompt to Ollama, and Ollama returns a generated response. In our case, it replied with, hello, how can I assist you today? Now that everything's working, we can go ahead and exit the EC2 instance shell. We won't be needing it anymore. Before we start up the front-end and back-end apps, let's quickly walk through the files used in our Langchain back-end application. Here, take a look at the API URL. This points to our FastAPI service running behind traffic on our EKS cluster. We also filter out the markup embedded in DeepSeek's response. We don't need that shown to users. You'll also notice that Langchain is imported in this code. Now let's switch over and check out our Streamlit frontend. We've imported Streamlit at the top, of course. Then we set up the title and all the logic needed to build the UI. You can always grab this code from the GitHub repo. The link is in the description of this video. Alright, let's start up the Streamlit application. We just need one command. Streamlit run app.py. Make sure you're in the right directory before running it. Give the app a moment to load. Now you can start sending prompts. Let's try something simple. Nice. The response comes through a bit faster than when we were running it inside a container on the EC2 instance. Try a few more prompts. And yep, everything's working just as expected. Now that we've confirmed the full setup is functional, let's clean up our resources. Remember to delete the load balancer, delete the node group, delete the EC2 instance we used to connect to the cluster, and please, delete the EKS cluster itself. You can also delete the ECR repositories and security groups. Although those won't cost you anything, it's good practice to tidy up. And that's it. Thank you for going through this project with me. We've successfully deployed and run a DeepSeek model using Ollama on a Kubernetes cluster powered by AWS EKS. All the code and documentation used in this project are available in the GitHub repository. The link is in the description below. CloudSpeed is your gateway to AI and the cloud. We make videos showing you the latest in tech, and we break down the real-world use cases. If you found this helpful, hit that subscribe button and tap the bell icon so you don't miss any updates. Thanks for watching.